This PowerPoint is about the structure of an atom. So by the early 1900s, scientists knew that an atom was composed of a nucleus, which contained protons and neutrons, and then outside the nucleus contained electrons, and as Bohr discovered that electrons are quantized, could exist only in certain energy levels. So this PowerPoint's going to talk about some of the details about atoms. This table at the bottom kind of summarizes things that you should know about each of the subatomic particles. The proton and the neutron have essentially identical masses, okay, a little bit different, but for our purposes, we're going to say they have the same mass. And the proton and electron have equal but opposite charges. So the proton has a +1 charge and the electron has a -1 charge. Of course, the neutron has no charge. We are going to assume that the mass of the electron is negligible. We're just going to say that the mass of an electron is 0, even though we know there is a mass. It's so small compared to the mass of the proton and neutron that we are going to ignore it for simplicity. What defines an element? If you look at the periodic table, you see all the different elements. What distinguishes one element from another? Well, that is the number of protons. So the number of protons, or the atomic number, defines the element. So if you look at the periodic table, every element has a number at the top of the box that's in, and that number is the atomic number. And our current periodic table is arranged by atomic number. Let's look at the atomic symbol we use for carbon, for example. If you look on the periodic table, you'll see carbon is atomic number 6. It's a 6th element shown, which means carbon has 6 protons. Every single carbon atom has 6 protons. At the bottom, you'll see the atomic mass, which we'll talk about a little bit later. And the symbol for every element is a capital letter, and the symbols are either one letter or 2 letters. Any symbol that is 2 letters, the second letter must be lowercase. You may remember in the early 1800s, Dalton was the first one to propose a formal atomic theory. And one of the 4 parts of Dalton's theory said that all atoms of the same element are identical. We now know that is not true. We can say that all atoms of a given element have the same number of protons because the number of protons defines the element. However, atoms of the same element can have different number of neutrons and therefore different mass. This is a really important concept and definition to understand. So atoms that have the same number of protons but a different number of neutrons and therefore different mass are called isotopes. It turns out that every single element on the periodic table consists of not just one isotope but multiple isotopes. For example, looking at carbon again, you can see here are 3 isotopes of carbon, and we know they're all carbon because they all have an atomic number of 6. And you may notice that when we draw chemical elemental symbols on paper, rather than on the periodic table, we switch places with the atomic number and mass. So in the periodic table, the atomic number was on the top. If you write it pen and paper, it's on the bottom. There's a good reason for that, which I'll tell you in a minute. But back to the isotopes of carbon. They all have the same number of protons, but they have different masses. So this top number are called mass numbers. The masses are different, and that's because they have different number of neutrons. So if you look at what we call carbon-12 isotope, and if you count, notice the protons are yellow. You can see there are 6 yellow balls in each of these 3 isotopes. The neutrons are represented by purple balls. You can see there are 6 neutrons in the first isotope in carbon-12, and in carbon-13, notice how we're naming these. The symbol of the element, then a dash, and then the mass number. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So those are all atoms of the element carbon, but they are isotopes of one another. It's important to understand there isn't one correct isotope. There isn't, they're all naturally occurring, and any sample of carbon that you take off our Earth will have a set ratio of all of the isotopes of carbon. And that set ratio will remain the same regardless of where you take the sample of carbon on Earth. From the elemental symbol and the notation around it, okay, so mass number, remember when we're using paper and pencil, not on the periodic table, the mass number is in the upper left, the atomic number is in the lower left. Atomic number is number of protons. What makes up the mass of an element? There are 2 particles that primarily make up the mass, and they are the protons plus the neutrons. That is the mass number. So make sure you know that. So how do we find number of neutrons? We have protons plus neutrons, and then we have protons. So how do we find neutrons? It's a subtraction problem, which now you can see why in pen and paper we put the mass number on the top and the atomic number on the bottom, because when you do a subtraction, you get the number of neutrons. Here's a simple example question. Magnesium, as all elements, has isotopes, and magnesium happens to have 3 isotopes. The mass numbers are 24, 25, and 26. See if you can write the chemical symbol with the superscript and the subscript for mass number and atomic number, and then determine how many neutrons are in each of those isotopes. So turn off the lecture and see if you can do it by yourself. If you look at a periodic table, you can see that magnesium has an atomic number of 12, and so all of the isotope or element symbols for magnesium must have 12 on the bottom. What goes on the top is the mass number. So remember, hopefully, that mass number equals the number of protons plus the number of neutrons. So we know how many protons each magnesium isotope has, and the question gave us the number of neutrons, so you simply add them together. One of the isotopes of magnesium had 12 neutrons, the problem said. So if you add 12, and 12, you get 24 as a mass number. One of the other isotopes had 13 neutrons, so again, if you add 13 and 12, you get 25 as the mass number. And finally, if you have 14 neutrons plus 12 protons gives you a mass number of 26. I mentioned this a couple of slides ago, but another symbol notation that you have to be familiar with is where you put the chemical symbol for the element followed by a dash and then the mass number. So neon has 3 isotopes. You may see it shown like this, neon-20. Remember, 20 is the mass number. Neon-21, okay? Or you can see, rather than the symbol for neon, it may be written out. Remember that if an element symbol has 2 letters in it, the second letter must be lowercase. I need to make a correction here. All elements have multiple isotopes that are naturally occurring. So even though isotopes have different number of neutrons and different mass numbers, they act chemically identical. And you'll find as you learn more chemistry that primarily what determines the chemical reactivity of an element is the number of electrons that an element has. So the fact that isotopes have different number of neutrons does not affect the chemical reactivity. So we have multiple isotopes of every element that occur naturally on our Earth, but they don't occur with the same abundance. So, for example, if you look at the 3 isotopes of neon, you'll see that neon-20, okay, is present. If you take any sample of neon out of the Earth, you'll see that 90.48% of that sample is neon-20. That only about 9% of the sample is neon-22 and less than 1% is neon-21. So this is called the natural abundance of the isotopes, and we're going to learn to take the overall weighted average atomic mass using these values. So there's some math coming up. Here's the formula for average atomic mass. So you'll probably want to jot that down so it's handy for you as you work these practice problems. So first of all, what is average atomic mass? I want you to pull out a periodic table now. And I want you to look at, for example, carbon. On the periodic table, of course, the atomic number's at the top. And you'll see a number at the bottom. Most of them have decimal points. So carbon's going to be 12.01. It may be more numbers after that, but at least 12.01. So what is this number? It's not mass number. That's the first thing to know. Now remember what mass number is. It's number of protons and number of neutrons added together. This, instead of being mass number, is average atomic mass of all of the isotopes. Okay? So they take all the naturally occurring isotopes, they get the average atomic mass, and that's what goes on the periodic table. Okay? So this is the average atomic mass of all of the isotopes. So the calculation we use is not a simple average. If you were to take a simple average, you would just average the mass, let's say for neon, 20, 21, 22. You add them together, then you divide by 3, and you would get the average mass of 22. That is not, we do not use simple averages to get average atomic mass, because we take into account the abundance of each of them. So the isotope that is more abundant is going to have more effect on the average atomic mass. So here's an example so you can get practice plugging into the equation. Chlorine has 2 isotopes that occur naturally, chlorine 35 and chlorine 37. Chlorine 35 is the most abundant isotope of chlorine and is present at almost 76%, whereas chlorine 37 is present only around 24%. Now, I want you to pay attention to something else too. We can go ahead and plug into the equation for average atomic mass, the equation on the last page. And what that told you is take the mass of an isotope, multiply it by its abundance in fractional form. So what I mean by that, instead of 75.78%, we're not going to put it in percent form. We're going to put it in fractional form, 0.7578. Okay. Now, as far as the mass, sometimes you're given two choices. So look at this symbol. It says the mass number is 35. That is the mass of chlorine 35. But then they give you another mass number which has more precision. If you're given two masses when you're calculating average atomic mass, use the one that's more precise. So 34.969, okay? And you do the same thing for all of the isotopes. So the mass of the other isotope is 36.966, and the abundance of the isotope, of that isotope, is 24.22. Move the decimal to the left 2 places, or divide by 100 to put it in fractional form. So you get 0.2422. And what we get for an answer is the average atomic mass for chlorine is 35.45. AMU stands for atomic mass units. That is the mass scale we use for elements and teeny tiny things. And that makes sense. So remember, one of the isotopes have a mass of 34.969. The other has a mass of 36. So you know that the average atomic mass has to be between these two numbers. You should also know which of these two masses the average atomic mass will be closer to. Since we've weighted the average atomic mass by the abundance, the average atomic mass is going to be closest to the more abundant isotope, which is here. So this number should be closer to 34.969 than it is to 36.966. So that's enough about mass numbers and average atomic mass. Let's talk about the electrons for just a moment. As I said before, the electrons are what determine the chemical reactivity, so they end up being very, very important. The number of electrons in a neutral atom, and all of the elements as they're shown on the periodic table are assumed to be neutral. So the number of electrons in a neutral atom is equal to the number of protons, okay? That means you have as many negative charges as you have positive charges, so that overall there's no charge. However, atoms can gain or lose electrons, which if they gain an electron, they get an overall negative charge. If they lose an electron, because electrons are negatively charged, they have an overall positive charge. So charged particles are called ions, another important vocabulary word. If the ion is positively charged, it is called a cation. If it is negatively charged, it is called an anion. Here's a visual for my visual learners like me. So if you have equal number of protons and electrons, you have a neutral atom. Then if you take away an electron, you're left with an overall positive charge, which is called a cation. On the bottom here, again, if you start out with a neutral atom, equal number of protons and electrons, and if you add an extra electron, your overall charge in that atom is now negative, which is called an anion. This lecture is walking you towards chemical reactions because they, as I said, they involve transfer or moving electrons around. And so if you remember the division of the periodic table, there's this what we call stair step. And hopefully you remember that everything to the left of the stair step are metals. So there are a lot more metal elements than nonmetals. Everything to the right of the stair step are non-metals. Nonmetals and metals react totally different. So metals tend to lose electrons. Remember what happens when you lose electrons? When you lose electrons, you end up with a positively charged ions. So if metals are going to make ions, they're going to make cations by losing electrons. Just the opposite for nonmetals. If nonmetals make ions, they tend to gain electrons, which gives them a negative charge, so they become anions, okay, usually. So if you look at the charges shown on the most common ions formed by these elements, you can see the metals end up with positive charges and the nonmetal with negative charges. And it's even more particular than that. The group 1 elements, the one in the very first group to your left, they're called alkali metals. They tend to lose only one electron, all of them. Every element down that first group tends to lose one electron, so every element in the alkali metals, when they form ions, form +1 charged ions. Group 2 tends to lose 2 electrons, so the ions formed by elements in group 2 end up with a +2 charge. A couple of other common groups that make the same charge ion all the time, the halogens, which are group 7A, that would be like fluorine, chlorine, bromine, iodine, those are the halogens. They're nonmetals, they tend to gain an electron and form -1 atoms. And finally, the oxygen family, they never gave it a unique name, it's called oxygen. So that starts with oxygen and then you go to sulfur and on down. Those all tend to gain 2 electrons, so they end up with a -2 charge. So you will ultimately have to memorize the elements that give you the same charge over and over. And so let me fill in what I just went over. Here is group 1A. And you remember in the last page I said they tend to lose an electron and end up with a +1 charge. Group 2A loses 2 electrons, so when they become ions, they have a charge of +2. Then we have all the transition metals in the middle, which are very confusing, and we're not going to go into how they become ions yet. They are metals, so they will make cations, but they make all different charges. They're not consistent. So now we go to group 3A in the old numbering system, or 13 in the new numbering system. They lose 3 electrons and end up with a +3. Carbon, the group right in the middle of the periodic table, can either gain or lose 4 electrons, so it can end up with either +4 or -4. The nitrogen group, now we're at nonmetals, and nonmetals tend to gain electrons and become anions. So the nitrogen group gains 3 electrons and so ends up with a charge of -3 when they become ions. Oxygen, as I said before, gains 2 electrons, and so all the elements in that group end up with a charge of -2 when they become ions. The halogens, group 7A in the old numbering system, or 17 in the new one, gain 1 electron and end up with charges of -1. Now, very importantly, look at group 8A. These are called the noble gases. And they are very, very stable. That's why they're called noble. They don't react. They want to be alone. They don't interact with other elements. And we'll learn about why later. But because of that, they don't tend to gain or lose electrons, and so they don't tend to make ions. So we'll just say they stay neutral. That is it for this lecture.